Hello, Robotics 10 students. Welcome to the second video in our series on the Net 1010 module, Digital Logic. Last time we took a look at the basic concepts of logic gates. And in that discussion, we were thinking of them as these kind of abstract concepts, these kind of black box imaginary systems where, what would it look like to have a box that has two inputs and one output, and the output changes based on the inputs by some predictable pattern. But those were just abstract concepts. Today, we're going to look at how we can actually build these logic gates in hardware using basic electronics components that you have in your electronics kits. Before we get into the logic gates, though, we need to cover one very important concept and component in electronics, and that is the transistor. So this is a picture of one style of transistor. This is the exact one that you have in your kits. If you're looking for it, you might have a few things that look similar to this, but look closely for the letters and numbers S8050. That is specifically the transistor that we're going to be using in this lesson. A transistor is essentially just a switch. It's something that allows current through or not, depending on some state. So just like the light switch in your room, it allows current through to the light bulb if you've flicked the lever up, and if you flick the lever down, it doesn't let any current through. Transistors work in the exact same way. They let current through if some condition is met, and they don't let current through in any other case. With transistors, what needs to happen for it to let current through is for another pin on the transistor to be experiencing a voltage. So it's an electronic switch that is triggered by more electronics. So in this picture here, this is the symbol that we use in schematic diagrams for transistors. And you'll see there's three lines coming out. Those are the three pins, just like there are three pins on the actual hardware. They're called the collector, the emitter, and the base. And this particular kind of transistor is an NPN transistor. We won't get into the naming or exactly what's going on inside this little box. What you need to know is that the collector and the emitter are kind of like the two sides of the switch. These two pins get electrically connected together or allow current to pass through them if the base pin is experiencing a voltage. So if the base pin is above some threshold voltage, then the transistor will allow current through the collector and out through the emitter. So this allows us to control signals or power to LEDs or other devices by changing the electrical voltage on a different pin from some other part of the circuit. So in our schematic diagram, we'll just quickly do this on a whiteboard. It's going to be a little sloppy. If I hook this up to a battery, around to here, to the collector of the transistor, and then out from the emitter, maybe I have a resistor and an LED, and then back to ground. If I just leave this be, the light's not going to turn on because our transistor is not activated. In order to activate the transistor, we need to connect this base to some voltage above its threshold voltage. And for the most part, we'll just consider positive and negative voltage. So if I could connect this to 5 volts, then it would allow the transistor to kind of activate or turn on and allow current through, which would turn on the LED. So one way to do that is we could just hook this up to a switch, like a slide switch, and it's got 2 positions, and one of the positions can be connected to 5 volts and the other can be connected to ground. And now if we switch this slide switch back and forth, that's going to be pulling this base pin either to 5 volts or to ground, which will either allow current through or not, which will turn on or off the light bulb. We have to be a little bit careful though. I've made one quick mistake here, and that is that we should always put a resistor here, because we want to also limit the current that goes into the transistor. The exact value that you use for this resistor is a little bit important because you don't want to overload the transistor, just like we have to make sure we use the correct resistor for an LED. But we won't bother going through the calculation or figuring that out. We'll just by default use one of your 10K ohm resistors. So this is a basic circuit just to kind of illustrate how a transistor works. We'll see later how we can combine transistors in interesting ways to actually construct the logic gates that we were talking about in the last episode. So how do we go from this to an actual circuit on the breadboard, and what do these transistors look like? So I'm here in Tinkercad circuits, and you see I have this transistor. One thing I need to note right now off the top, the transistors that you have in your kits, the 8050s, they have a pinout that looks like this. If we're looking from the top with the flat face forward, the emitter is on the left and the collector is on the right. Now, Tinkercad Circuits only has one type of NPN transistor built in, and this is specifically a 2222. And one big difference is, and you can see the labeling here, the collector is on the left and the emitter is on the right. So it's the opposite of yours. So when we get to making this on the breadboard here in Tinkercad Circuits and you're making it yourself, just make sure you have your transistor flipped 180 degrees from how I have it. So this is the transistor. I'm going to just zoom out a little bit and show you this circuit right here. So this circuit here is this exact circuit that I had on the whiteboard. We'll just flip back to it for a second. We'll remember that we have from the 5 volts, we're both going to one side of this slide switch, and we're also going to the collector of the transistor. And then the other side of the slide switch goes to ground. The emitter of the transistor is going to a resistor and an LED. And then the middle pin of the slide switch goes to a resistor and then to the base of the transistor. So this is how that looks like on the breadboard. I've done it nice and spaced out so you can see what's going on. You can see I've got from positive going to one side of the slide switch and going to the collector of the transistor. Remember to flip your transistor around 180 degrees, so it'll actually look like this for you. And then from the emitter of the transistor, we're going through a resistor to limit the current, to an LED, and then to ground. We're also going to ground from one of the other legs of the slide switch. And then the middle pin of the slide switch is going to a resistor and into the base of the transistor. So now that I have this hooked up, I can start the simulation and we can see if I have the slide switch switch to positive, my light is on, and if I switch it to negative, the light goes off. And that is because this switch is turning on and off this transistor. Now in this very simple example, there's no real need to have this transistor here. I could just have this switch directly controlling the LED. The point of this exercise was just to describe how a transistor works, because the stuff we're going to see next can't just be handled by simple switches. I recommend that you actually build this circuit on your breadboard and make sure that it works in the same way that mine is working, so that you know that you're hooking up your transistor correctly before we get into some more complicated circuits. Another thing to note is the resistor you use for limiting the current on your LED. Usually you should use the 220 ohm resistor so you get a nice bright LED. For some reason, the Tinkercad Circuits simulator thinks that that blows up the LEDs here, so I have to use a 10K ohm. But also make sure you use a 10K or even a 1K is fine for the connection from the switch to the base of the transistor. Because again, we do not want to overload this transistor. It could get hot. It could also just stop working. So just be careful about that. Make sure you've kind of set things up properly before you connect power to the Arduino. And once again, one more reminder, your transistor needs to be flipped 180 degrees. So the flat side in this case would be facing away from the rest of this circuitry so that you have the correct pin connected to the right spot. So now that we know what a transistor does, we can start thinking about what can we do with transistors. Now, some of you might know that your CPUs are essentially built of billions of transistors. And that's really what's going on inside of a CPU is a bunch of logic built up of these chains and interesting, clever arrangements and connections of transistors. But to start off, we can just think about how do we construct those basic logic gates. This website here from Hyperphysics shows how you can construct basic logic gates from transistors. So here's the AND gate. And if we look, we can use 2 transistors here hooked up in this way and have an input and a single output. And so if we hook this up on the breadboard, we should see the same behavior that we talked about in the theoretical model of the AND gate. So this output should only be on if both inputs are on, A and B. And you might be able to see how this is actually working. Input A is driving the base of this first transistor. So current is only allowed to flow through this if input A is on. And input B is driving the base of the second transistor. So current can only flow through here if input B is on. And so if only one of these 2 is on, current might be able to flow through here, but then it's stuck. Or if just B is on, current can't even get through A to begin with. But if both A and B are on, it can flow through here, and then we've got voltage here on the output. And then this last resistor is just making sure that we still have 5 volts here and we're not shorting before we get to ground. So let's figure out how we can construct this on the breadboard. I've actually got it already built here in Tinkercad. This is my version of it. It might be a little bit hard to look at, might look a little messy at first, but let's just take a close look here and see if we can decipher what's going on. First, let's look at this chain of the transistors. So we'll look at our diagram again. We have to go from positive to the collector of one, and then out of its emitter directly to the collector of the next one. And then out of that emitter goes to our output, as well as another resistor to ground. Let's take a look here. We're going from positive to the collector of one transistor. From the emitter of that transistor, we go to the collector of the next. And then from the emitter of that transistor, we're going out to here. And this is that resistor that's going to ground. And I also now am just showing you the output using a resistor and an LED, so we can visually see that. Now that output could go to anything else. We're just making it a little bit visual here by having the LED and the resistor connected to where the output is. The rest of the circuit needs an input through a resistor to the base of the first transistor, and then an input through a resistor to the base of the second transistor. So in the circuit, we're just using our inputs as these switches, but of course these inputs could come from anywhere else. They could come from other logic gates or other pieces of hardware, but for demonstration purposes, we'll use these switches. And so again, very simply, one leg to positive, other leg to negative, and then the middle leg is going through a resistor to the base of the first transistor. The other slide switch is set up in the exact same way, and it's got its middle leg connected through a resistor to the base of the second transistor. And of course, I've just noticed an error here. I had this leg of the LED plugged into the wrong row. Of course, it's got to be plugged into here for any current to make it from this resistor out to the LED. So I've got it plugged into the Arduino, and let's take a look at the behavior. So right now, both my switches are on. They're connecting the positive to this green wire and the positive to this green wire. So this is like we have input A on and input B on, and we can see our light is on. If I have only one of them on, the light goes off. If I have them both off, the light is off. If I have the other one on, the light is off. The light is only on if both of these are on. So that is a simple AND gate that we've created on the breadboard. It looks a little complicated, but remember, a lot of the complexity here is just so that we can control these inputs and see visually the output. Really what's going on, just this chain of these two transistors, is fairly simple, but it does take up a lot of space. And when we're working with logic gates, we don't want to have to recreate the logic gate every single time, especially when you consider projects getting bigger and bigger in complexity that might need 8, 10, 20, 50 different logic gates in order to work. It just isn't feasible to build it out of this kind of transistor. The truth is that over the years, we've found ways of making transistors smaller and smaller and smaller to the point where we can jam a billion into a little CPU. But also for this scale of electronics, we have products that give us logic gates that are kind of already packaged together and built in so that it's easy for us to use them for the kind of things that we need to do. And one way of bundling a known circuit of electronics into a consistent and manufacturable little package is with these little things called ICs, or integrated circuits. You have a handful of these in your kits. I've added some more in addition to what came in the kits originally. But what ICs are is essentially just a little black box that has inside of it some very, very small electrical components arranged in a specific circuit. Now, there are thousands of different varieties of ICs. Each kind has its own specific circuit built into it. And we're going to look at a handful in this class. The first one that I'm going to introduce you to is the 7408s and the 7400s and 74. There's a handful of other ones. And essentially what these are a collection of logic gates built right inside these little chips. So it makes it very easy for us to quickly build circuits that are made up of a handful of logic gates. The 7408 that I'm showing you right now that you don't actually have in your kits, but we'll get to one that you do in a second. This is made up of 4 AND gates. I'll show you a picture here. This is a representation of what's going on inside of this little IC. And you can see this is the symbol that we saw in the last video for the AND gates. And there are 4 of them built into this chip. Each one has 2 inputs and an output. And there's also some pins on this chip for VCC, which means positive voltage, in our case 5 volts, and for ground. It's pretty amazing to think that inside this little chip that's this size, they have stuffed 4 of these circuits. And what's really nice about ICs is that if you know the number of the IC, you can look up the data sheet like this one. This is what we call a pin out or a pin diagram. And you can know exactly what each pin does and how you can hook this up. So let's hook up that last circuit that we did to just test how an AND gate works with our AND gate IC. And then we'll get into the one that you're actually going to use for your workbook. So here I have it already connected. I've basically just replaced those transistors with this IC. And let's talk a little bit about how you can connect things to an IC. First of all, they're built specifically so that they fit nicely across breadboards like this. This is a standard width. This package type is called DIP, dual inline pins, which just means it's got 2 rows of pins on either side. And that's typically at a standard width so that it will fit in a breadboard and other standard size electronics assembly hardware. And before we really look at how I've got it hooked up in here, let's take another look at the data sheet and we'll just look at a few things. First of all, let's remember that there's this pin here. Pin 14 is for 5 volts and pin 7 is for ground. Now, how do I know which pin those are on my actual IC? How do I know which way around is the right way around? Well, if we look closely here on the IC, there's this little notch. There might also be a little circle here. There will always be some kind of indicator on one side of the IC telling you which side is up. On our diagram here, we also get a little notch here that tells us this is that top side. And when we know the top side, we can look at this corner beside it, and this corner will always be pin 1. Then we'll always count up, down this side, and then we'll wrap around and continue counting up back the other way. So we kind of work our way around the pin with numbers, starting with 1 and going up to, in this case, 14. But there are ICs with different numbers of pins, but the way that we number them is always the same. So you can see in this circuit here, I've got pin 14, which is the last one all the way around here, connected to my 5 volts. And I've got pin 7, which is the one on this corner here, connected to ground. That is because I've learned that from looking at this pinout diagram. That gives power to this whole system so that it can actually work. Now, the rest of the connections are to do with these AND gates built in. And you can see there's 4 AND gates built in. This is what's called a quad AND gate IC. And it doesn't matter which one you pick. I've chosen just to use this top left one. And if we look here, it's got input 1 and input 2 on pins 13 and 12. And then the output comes out on pin 11. So I've hooked that up here. I've done the inputs in the exact same way with these slide switches connected to power and ground. And then the middle one through a resistor into this pin here, which is this input number 1. And I've got the other one connected through here, through this resistor to this pin, which is input number 2. And then our output is the next pin in the row. And that's coming out here back again to the same circuit where we just had this one resistor that allows us to measure 5 volts here, if that's something that we need. But I'm also visualizing that signal by connecting a resistor and an LED here. And what we should see is if I start the simulation, it works in the exact same way. So we can see the light is on when both of the switches are on. If I turn either switch off, the light goes off. And of course, if both switches are off, the light is also off. So what's great about this is that we've saved a lot of space. Because remember, before we had 2 transistors here taking up a bit of room, and probably about the same room as this chip, but we actually have 3 more AND gates in here that we could use if we needed. So it's a lot more space efficient, a lot less setup. You don't have to remember, how do I make an AND gate out of transistors again? You don't have to remember any of this. We can look and see how you can set up an OR gate using transistors a little differently, how to make a NAND gate. It's just the opposite of an AND, of course, and a NOR, and another version of NOR. And you could make XOR and XNOR, all from transistors and resistors very simply. But the truth is, we never do that. We usually just turn to using an IC because it's easy, we know it's going to work, and we get some extra space out of it too. So you could go and build this on your breadboard, except for the fact that I did not give you any 7408 ICs. You do not have any quad AND gates, but that's okay. What I did give you is a 7400. And this IC is very similar to the 7408, but instead of having 4 AND gates, it has 4 NAND gates. So here's what the pinout looks like. I found this picture just by searching on Google, 7400 pinout, and there are many, many diagrams. I just grabbed this one because it's got nice colors so you can see it very clearly. And it's essentially the same thing as the 7408. Even the pins are arranged in the same way. But instead of AND gates in there, these are NAND gates. And so exactly the same power on 14, ground on 7. And for this one that we were using, the inputs on 13 and 12, and the output on 11. Exactly the same structure, which is handy for this example here, because it means I can just remove this, plop this in to the same spot, start my simulation, and now let's see if that behavior is still true. Now, both of my inputs are on, which for an AND gate would turn the output on, but remember NAND gate is just the opposite of AND. So in this case, AND would be on, NAND is not on. And if I turn one of the switches off, our light comes on. If I have the other switch off, our light comes on. If I have both switches off, our light is on. So that is the exact opposite of the AND gate. So we know this is now working. So that's excellent. And this NAND gate is what you're going to use for a few more of the exercises in your workbooks. And I'll cover that in the next video. What I want you to do for now, try building this circuit. First, try building some of those circuits with the transistor. And if you're curious about how to make some of the other logic gates out of transistors, you can find this website. You can just search for logic gates out of transistors or logic gates transistors. This is a great page, Hyperphysics. So if you find that one, that's a good resource. But there's lots of other examples that will give you these circuit diagrams, and you can try yourself and figure out how to build that on the breadboard. Next time, we're going to look at what can we do with multiple logic gates and combining them in interesting ways to make some pretty unique stuff happen. And then down the road, we'll look at some other ICs that do some very different things from just these basic logic gate ICs. And then I'll turn you loose to just make something interesting. And that is basically the module of Net 1010 and where we're going to end our semester this year. So there's lots of other stuff in your Arduino kits that we didn't even touch. A lot of it we cover in Robotics 20, so do hold on to those kits if you're thinking of taking Robotics 20. Some of it we're not going to cover at all, but it's there for you to tinker with and explore with, find some tutorials online. But for now, let's play around with some transistors and some ICs. So I'll catch you next time. Have fun.